Now, when we did exponents and you were solving, if you had something like 3 to the x plus 1 equals 3 to the 2x minus 3, then you ended up solving, you had the same base, you ended up dropping that and using x plus 1 equals 2x minus 3. We're going to do something very similar for logs. We're saying if you have the same two bases in your log, then the two arguments must be the same. So let me show you here just to illustrate this to you. If I have log base 7 of x, this is not the situation here. I'm going to write this down wrong on purpose. If I was to look at this and say, oh, look, I have log base 7 for everyone, so this means I can drop all the logs and go x is equal to 45 minus 9. It does not work that way. It is only when there is exactly one logarithm on each side of the equation. So you have to use log laws to pull these things together, so that's all that you get is log equals log, nothing else. No numbers, no logs, no exponents. Same way that up here, you can't do it if all of a sudden you had, times 3 to the x. You'd have to add those exponents together. You couldn't just drop them at that point. Okay? So here's how we combine them up. This would be log base 7 of x is log base 7 of 45 over 9. So that means now I'm in the situation where I have the same base and there's nothing else but those logs. So I know that in order for that to be true, x must be equal to 45 over 9, which of course is 5. Okay, so in the next example, it's very similar. All I want is one single log, so you can just use your log laws to combine these. And now I'm in the situation that applies. Log base 7 is the only thing on both sides of the equation. That can only happen if 4x equals 12. X must be equal to 3. Now the absolute worst that it gets is when it looks like the next one. The next one's really not that bad. It's a grade 12 log laws plus a grade 11 quadratic equation. Let me show you how it works. If I put them together, this is log base 5 of x plus 1 times x minus 3 equals 1. Now you might say, well, uh-oh, how do I drop this now? There's only one log. Well, there's two ways to do it. Number one is the way I'm going to suggest you do it because it's the way we've already practiced it. You can rewrite this as 5 to the 1 is equal to x plus 1 times x minus 3. Or, I don't know why, some people like doing it this way, and that's perfectly fine with me. You could also rewrite it like this. And this kind of something tricky. Not something people always think about immediately, but if you think about it, this here, log base 5 of 5, that is actually equal to 1, which is what I was replacing over there. That's why it works. They're equal. 1 is equal to log base 5 of 5, so I made that replacement. Now I can drop them, which means the logs would be gone. I'd have x plus 1 times x minus 3 equals 5. Both are perfectly acceptable ways to solve. I am going to continue on doing it this way, rewriting it as an exponent. Okay, so that's how you could do it either way. When you have log, that means you can drop them when you have a common base, or you could rewrite it as an exponent, which is what we did here. Okay, so 5 is equal to x squared minus 2x minus 3. So x squared minus 2x minus 8 equals 0. X minus 4, x plus 2. So x equals 4 or negative 2. So like I said, once you get past the log laws, now we just have a quadratic equation to solve, which you should be deadly bored of since you've done it now for a couple of years. However, there is one caveat that comes along with logarithms. Does anybody see a problem with using x equals 4 or x equals negative 2? the logarithm cannot be negative. Now remember, that doesn't mean negative 2 is the wrong answer just because it's negative 2. It means that when I put it in, it becomes negative 2 minus 3. That's negative 5. Won't work. So whenever you check your answers, it's when you stick it in. Negative 2 plus 1. Negative 1 won't work. That's the negative that you can't use. It's not that the answer is negative, it's that when you try and use it inside the logarithm, it's negative. That's where the problem happens. Okay? And similarly, 4 might not work. You have to check by looking at those two and saying, if I put in 4, that's okay because that's a positive number. And that's okay, so 4 is an acceptable answer. So that's how we would finalize our answer there, is we would reject negative 2 and we would keep 4 as our answer. Okay, so that's the only thing that you have to be careful of dealing with logarithms as opposed to just a quadratic equation. You have to check that your answers make sense before you put them down as your final. Okay, so you have a look at this next example. See if you can spot the problem. If you do spot the problem, resolve it correctly. So what do you think? What was the mistake that was made? Yeah, there is a problem on the second step. What happened that went wrong? Yeah, so the logs were dropped early. Remember, that's like the most common problem is people will say, oh, look, I have the same base everywhere, so let's just chuck the logarithms away. It doesn't work that way. What should have happened is I had log base 2, use the log laws to combine them. That's the step that they should have had next, and then you can get rid of the logarithms. X plus 4, oops, times x minus 5 equals 7x. So that gives me x squared minus 8x minus 20 equals 0. And I can factor that to negative 10 and 2. Thanks. Nice to know you got my back. So my answers then, 10 and negative 2. What do you think? Good. 10 will work. If I check, no problems there for 10. No problems there. So 10 works. But negative 2, it's okay here. Does not work there. Does not work there. As soon as it doesn't work in any part, it's done. Reject negative 2. Our answer should just be x equals 10. Okay. So if you're getting the hang of it, what mistake was made here? Resolve it correctly. All right, so what did you find? What do you think the mistake was? Second step again? Yeah? Okay, how come? What happened? Right, so there wasn't just 2 logs. You have to combine everything. All you can ever see is log something That's it. If anything else appears in the problem, it's not ready to solve yet. You have to use log laws to get there. So what we should have done to start is go use the log law to move that exponent up and get log of x squared equals log x squared plus x minus 12. And the good news is, if that's what you did, this is a lot easier to solve. So let's see here. You just have, well, I guess I might as well call that 0 equals x minus 12, so x equals 12. Okay, we still have to check. No problem there. If I put in 12 here, that's going to be like 144 and 12 more. It's way bigger than that, so it's works there too. So that is in fact my answer. It would be highly unusual that there would be no answer. I'll just tell you from experience, generally there's something to reject. There may not be, but generally there's at least one answer. If you found that you didn't get any, you might want to double check it, but it could happen, but it'd be highly unusual. Usually there's at least one that works. Okay, so now we're just going to say forget about correcting people's mistakes. Let's pretend you're actually going in to solve some log equations, something that could possibly appear had you had to do this on like a quiz or a test. Okay? Okay, so in this case, I have a solution of x equals 3, reject the negative 1, and x equals 8 over 5. When I double checked, for example, up here, what I'm looking for is that it's got to be bigger than 15 out of 5, because that's 3 of them here. Here I was looking for, so 125 would be 5, and it is bigger than 125. So, you know, if you're trying to figure out how would you do it without a calculator, you're just trying to make fractions, figure out what the fraction would be. Hopefully you have a nicer number to work with than a fraction, but if you blank out, don't feel like you can't ask me to do that for you on a calculator, since I'm supposed to be testing your knowledge of logs, not your fractions knowledge. So, one other caution to you, you have to be very clear to me what you're rejecting. So you either need to cross it out, reject it, circle what's correct. Be very clear so that I know that you've actually taken that out of your possible answers. Because not only is that incomplete, it's actually incorrect if you didn't reject part of it. So put a box around it or write reject, however you want to do it, but be very clear about what answers you're keeping. Okay. Now the next one, let me just give you a little bit of background on it before we start. The next one here, you know, it's there because there's nothing wrong with you doing this, and some students are like, hey, I have no problem with this. I am ready to go. Let's solve it. Because what you're going to end up with here is a rational equation, something that looks like this. And right now, some of you just cringed and goosebumps ran up the back of your neck because there's a fraction in this equation, right? So let me just show you how to make life easy then. If you don't want to work with the fraction, manipulate the log laws in your favor. If I move this to the other side, then what I would end up with, maybe I'll do it in purple here, log base 4 x plus 1 is equal to log base 4 of 8 plus log base 4 of 2x minus 3. Now when I do the log laws, I don't have a fraction anymore. I'm going to end up with x plus 1 is equal to 8 times 2x minus 3. So either way, you're not really saving yourself any time. You're just avoiding that fraction if that makes you, you know, not so comfortable working there. Okay, so just know that when you do go to solve them, it's like the exponent laws. You have a lot of freedom in how you choose to manipulate it, so sometimes you want to do it in your favor. If you don't like the fraction, make it a positive so you're multiplying instead of dividing. Okay, so we might as well finish this one off really quickly. The one in red, if I did a little bit of math here, I'm at the same point now. They're the same amount of work. It's just that I didn't have a fraction to deal with. So I'm going to have x plus 1 is 16x minus 24. So negative 15x is negative 25. So x is going to be 5 out of 3, which works out. If you double check it, that is the possible answer there. Okay, so for the next example, again, this is one of those things where, you get in some confidence and you're like, yeah, it's not so bad. I can do these log laws. It's working for me. And then, boom, something like this hits you and you go, uh-oh. How do I deal with a 1/2 in my problem now? Oh, man. Can anybody think of a way of writing this so that we don't have a half? We have a log in there. Change 1/2 into log. That's exactly what we're going to do. Can anyone be more specific? Log 9/3. So remember, when you're saying, someone's asking about logarithms, they're really asking about an exponent. They're saying, what is the exponent? And you're telling them the exponent equals 1/2, right? So if I put it into the log, 9 to the 1/2, that's 3. So I could rewrite this as log base 9 of x plus log base, oops, sorry, that's an equal sign, equals log base 9 of x minus 1 plus log base 9 of 3. So there may be times when you need to do something like that. You've got a number, and in order to use the log laws, you have to turn that number into a logarithm. So let's just finish this one out then. Log base 9 of x is equal to log base 9 of 3 times x minus 1. I'm sorry, so I can drop the logs there. So negative 2x is negative 3, so x is 3/2. And again, if you double check, that works for all the ones in that equation. Okay, so scary? No, honestly, it doesn't get any worse than that for log equations, and that is typically one of the if you want to know, am I on the right track with log laws? Am I on the right track with equations? That's it. If you're comfortable there, you're going to rock your next quiz. There is one thing here that we need to do, which is a little more algebraic, so don't let it scare you. It's the same thing. It's just you have to take a deep breath. Every time I see one of these, even me, I'm going to take a deep breath and know that I got to commit to this. It's going to get ugly, people. Don't worry. We're going to fix that, but it's going to get ugly here. So just hang in there for a minute with me when we do it. How do you solve an equation like this? Anytime you're looking for an exponent, and that's where the missing pieces are. Missing piece, missing piece. If you're looking for an exponent, you want a logarithm to help you. So to do that, what I'm going to do is log both sides. This works, by the way, with the other exponential equations we did where the bases can be made the same, but why you'd ever want to do that, I don't know. Okay? If you can't relate them, like 5 does not become 9 in a nice way, then this is the way to go, is log both sides of your equation. Now, why is this helpful? Watch what happens on the next step. I don't have an exponent to worry about anymore. The exponents can be pulled to the front, so now I don't have an exponent. I actually just have a product there. It's x is in the front. It's like a coefficient. Oops, I forgot the 9 there. Now sometimes it starts to look really messy because you got all these x's and logs in there, but just remind yourself, all this is a number. If you put this in your calculator, these are just numbers. Don't let it freak you out. It might as well be like 2 times 5 or x times 3. It's the same thing. You just have to, work past that. And if I'm going to solve this, what you normally do when you solve an equation, right? You move all your x's to one side. So let's do that. We'd have x log 5 minus x log 9. And you'd have all your constants over here. So there's one of my constants. Now how am I going to get x by itself? What can I do? I got two x's and you're... Yeah, factor it. So if I factor it, now I only have one x in this problem. So I can solve for it. Just divide by log 5 minus log 9. And this is all something that the calculator can give us for an answer. If this was a non-calculator portion, you just leave your answer now and walk away. If we do need to use the calculator for it, we can punch those in and get a decimal answer for it. So for our lesson, the purpose of our lesson, I'll assume you know how to use your calculator by now. We'll move on. But if we wanted a decimal number, simply just put it in the calculator from here. So try the next one. It's the same technique. Take a deep breath. Know that it's going to go from this little exponential equation and get messy and turn into a fraction at the end. But give it a try and I'll catch up to you. Now the messier it gets, the more I got to recommend you use brackets to remind you. So don't be, to make sure you don't make a careless mistake, the whole thing is moved to the front. I always put a set of brackets in there. And remember, this has to be distributed, so both pieces need to be multiplied. So I'm going to end up with 4 pieces here when I'm done. I'll have 3x log 6 plus log 6 is x log 8 plus 3 log 8. And now, like every other equation, when you go to solve it, x's go to one side, constants go to the other side. And now I'll factor out x. And I can divide to get rid of that, that factor there. So it looks pretty messy, but again, it's something I could just give to my calculator. It'll give me the decimal number that I'm expecting to solve that equation. All right. Any questions then? Anybody freaked out by it? Yeah? Good question. You cannot, the only thing you can take out when you divide in a fraction, you can't do that. The only thing you can do is if you had factors, like if it was 3 times log 8 minus log 6. If it was like this, then yes, because those are factors, you could cancel them out. But this is just one term that has a 3. It has to be the whole thing would need a 3. That's what you're missing is this piece here does not have it. Right? The first one would get it when I multiplied through, but the second one is missing it. There's no 3 here. Happens more often than you think. So in this case, no, you can't cancel out those 3's. Great question. Anything else? Okay, so let's try the last set of applications then, just so you have a chance to see how this works. A culture of bacteria is initially 300 in size. After 2.5 hours, there are now 1,000 bacteria. What is the doubling time? So usually in practical terms, that's the way we talk about it. Like the half-life, the doubling time. So let's make an equation for this, and I'll show you how we can set it up to figure out doubling time. Now, doubling should imply something to you. When you think of doubling, what's the number that comes to mind? Genius. Nice. Okay, we're off to a good start. So what I'm saying then is that's the number I want to keep doubling. So my exponential equation is going to be in this form, right? Double the number. So what I know about it, though, is I start with 350. I start with 300. And after 2.5 hours, there are 1,000. So 1,000, I started with 300, and I doubled it. Every 2.5 hours. Or sorry, my apologies. I've skipped a step here that we need to talk about. If I was to do this, that's correct, but that would happen in, we talked about this before, I'm not sure why I decided to skip it here, but in 2.5 hour increments of x. So if I want to know, I don't want to know what it is every 2.5 hours, I want to know the hourly increments, then it should look like this. X divided by 2.5. Does that look familiar when we had to do this before? I hope. Well, like normally it'd say like in 5 days, and then we would have to convert it to this divided by 5, right? Because right now, if you told me, if you gave me 5 hours worth of time, that's 2.5 hour periods. So that's 5 divided by the 2.5. So this is the equation I'm dealing with here. And I want to know how long it takes to double. So just this. Oh, okay. My apologies. I was right about being wrong the first time, but I was wrong the second time as well. Sorry to confuse. I'll clarify it right now. The problem was if I'm going into doubling time, 2.5 hours has elapsed. I don't know how long it took to do that. So for example, I want to know how many times it doubled. I need to know what the bottom of this fraction was in order to figure out how many times 2 was applied. So for us, I'm going to put a p there. One way you can think about your applications is they take this form where A0 is the initial amount, C is the growth factor, like how much it's, or it could be decay, and T is the elapsed time, and P is the growth period. So we've already seen this. For example, like I'd said earlier, if we told you something about how much a population grew in 5 days, the period is every 5 days from the information you got. This time it's reversed though. We don't know how long the growth period is, meaning we don't know how long it takes to double. That's why we're trying to find the amount of time it took to double this population. Okay, so now we'll need logs because I'm trying to figure out what the exponent is. So we'll rearrange this. 1,000 divided by 300 is 2 to the 2.5 over p. And I can knock a few zeros off this. That's just 10 over 3. So log in base 2 of 10 over 3 is equal to 2.5 over p. All I did here was rewrite. This is an exponential. I'm rewriting the exponent as a logarithm. That way I get my exponent out of there, and I can solve without having to have it at the top of this 2 here. So now if I need to solve for p, p is equal to 2.5 over log in base 2 of 10 over 3. Now, if you don't have one of those really cool calculators that can do this log base 2 for you, remember the change of base rule. You can make it any base you want, where the old base goes to the bottom and the argument is at the top. Okay, so for me, that's going to be 2.5 divided by, and it's the log of 10 over 3. Divided by the log of 2. So it would take approximately 1.44 hours to double. Okay. So that's one thing that'll be handy for you to refer to when you do your exponentials. That is going to cover all your growth and decay formulas that you'll work with here. So let's work on it then with a radioactive material that is 60 grams, and a scientist estimates it will weigh only 40 grams in 450 years. So we want to know what's the half-life. Okay. So first of all, just see if you can set up an exponential equation to model the situation. Okay, so see if you know where to fill in these values for the exponential equation. So can we think of an equation then? What would it look like if I wrote this out? Yeah, 40 equals 60. What's the growth constant? Yeah, a half, or 0.5. And I'm going to have time elapsed, and I know this is every 400, sorry, I know it's 450 years that have gone by, and I want to know how long does it take to have this substance? What's the growth period? So these two things are what are directly connected, the growth constant and growth period. If you're trying to figure out where does the time go on this fraction, this is always the amount of time that has gone by, or time that has elapsed. So what you need to ask yourself is this the time that's gone by, or does this number connect to the growth constant? In this case, it tells us in 450 years. We know that's how long has gone by. It has nothing to do with the growth constant of 1/2. Okay, so I end up with a half-life of 769 years. Okay, so as far as your practice goes in solving log applications and equations, this is where you're going to start your practice.